Alright, so what we're going to do now is a video here on the current carrying wires. So as it sounds, this is just a wire with electricity running through it. So moving charges. You can also apply a lot of what we're about to talk about. It doesn't have to just necessarily be electricity flowing through wire. It's pretty much any charges as they move. We're going to essentially take what we talked about in the last one about the charges and the forces on them and the way the magnetic fields and stuff work, and we're going to kind of extend it out to a whole bunch of charges moving at the same time. Okay, and we're also going to answer the age-old question here eventually, probably in the next video, about which way charges actually flow when you have current. So far we had to assume that it went in the direction of the positive charges. Of course, I think we all know now that it's actually the negative charges that move, but we're actually going to show or explain the experiment that showed which it was. So it's pretty much identical in every case except one. So anyway, what we're going to have here is we're going to have a new right-hand rule, and I'm going to try and draw this. This is a wire, all right? So this is like a wire that's coming toward us, right? And so, something like that. Here's a wire coming toward us. Okay, goes off, kind of far back in that direction. All right, and so we have a wire, and in this wire we have electrical current. We'll say it's going that way. And what does this do? Well, moving charges are affected by magnetic fields. Stationary charges or charges moving parallel to a magnetic field are not affected by it. Well, it turns out that it's not just that moving charges are affected by magnetic fields, it's that moving charges create magnetic field. So we had magnetic fields affecting moving charges, and now we've got moving charges creating magnetic fields. Okay, and it turned out the way it creates magnetic fields, if we have a bunch of charges moving in a straight line, so this would be a bunch of positive charges in the direction of current, right? It's a whole bunch of positive charges all flowing this way. It turns out it actually makes this into circles. It makes like loops around the wire, like that. So you'd have these these circular magnetic fields around the wire. If I draw the wire sideways like this, it's these loops. They're perpendicular to the wire, so it'd be more like kind of like that kind of thing, where they went around the wire like that. Okay, something like that. So this would be with the current running that way. And then if we changed it one more time where the current was coming toward us, so this is the wire and the electricity is coming out of the screen towards you, what it would essentially do is make loops that look like this. And of course up close this field is stronger, but as you get further away you have to space those field lines out more because it makes these concentric circles, but it gets weaker. So something like that, where this is the wire right there coming towards us and the current coming towards you, but it makes these concentric circles around the wire as electricity runs through it. How do you tell which way? Because you can imagine that is this going to go around it clockwise, or the arrow is going to point counterclockwise? How do you determine this? And the answer is our next right-hand rule. This is our right-hand rule number 2. So right-hand rule 2. And for this one, what you do is you point your thumb, so thumb in the direction of the current of I, and then your fingers, if you were like grasping a hold of it, like you were grabbing the wire, your fingers will wrap around it in the direction of the B field, the direction that it's pointed. And so I have another little picture to show you to show this. So there you go. So you see here's the charge moving up this way, out of positive into negative. There's our current going up. You can see the thumb pointed up in the direction of the current, and then the fingers are wrapping around that way. If you were looking for from above, from top down, it'd be counterclockwise. And you can see the arrows are wrapping in the other direction. If the current were reversed, then his thumb would have to point down, right? be pointed down, and then the fingers would wrap the other way. From looking from above, they'd be wrapping clockwise, and all of these arrows would flip and point the other way. All right, so that's the right hand rule number 2. It's the direction that the magnetic field wraps around a current carrying wire. Now, we don't need to know this for this course, but I thought it was good to kind of show because it's a bit interesting. But you don't need to use this equation or have to know how to use it. But the magnetic field created by a straight, essentially infinitely long current carrying wire, so just a really long current carrying wire compared to how close we are to it. So in other words, the wire is a lot longer than the distance we are away from the wire. And what you get is this. Now, if you remember from the videos before, well, we had some of those, those cross product things, right? Where we had the del cross B was equal to mu naught J, where this was the current density. Really J is the current density, so current per, and it's usually like a line density or a volume or something like that, or current per area, or current per length is usually the one used for a wire. Well, anyway, you can use this right here and actually go through and do some calculus on it, and you can get this result here. Mu naught I, the J just becomes an I, and you're left with mu naught I 2 pi r, and this is the equation for the magnetic field strength different distances away from the circle. If you notice, this is, I think, our first time seeing this. We have a field strength that's dropping off as 1 over r and not 1 over r squared. And the reason for that is every time we've had this 1 over r squared, it's been a situation where we had spherical symmetry. But here we don't have spherical symmetry. Here, if we take a cross section of it, like if we're looking at it on end here, we have a circular symmetry. We have all these circles formed. And so, if we cut down one little cross section, you know what I mean? Like we came in here and cut a little sliver, right, out of that right there. We just cut that slice out right there of our wire. Well, then there'd just be, some charges right there moving, and then we'd have just a circular situation going on, and all we're really doing is looking at the charges passing through that area at any time. So it is that circular symmetry that we get from this line, and we end up with a 1 over r dependence instead of the 1 over r squared dependence. So it doesn't get, the strength of it doesn't drop off as quickly as it would with the spherical symmetry. But I just wanted to point that out to you because not everything is a 1 over r squared symmetry. It depends on the symmetry of the situation. In this situation, circular symmetry. Okay? But anyway, not the 1 over r squared. So now let's take this and let's extend this out a little further. What happens if we take a wire like this and we take this straight wire and we curve it into a loop? Okay? Pretend that's a better loop than I made. But we make a nice loop out of it. Well, if you think about it, we can do the right-hand rule at different places. So let's say electricity's coming in this way, so it's going this way, and it's going around the, oops, I'm sorry, those are backwards. Let me erase that. Let me just try this whole little drawing again. Okay, so let's take and say, all right, we have our loop comes in, goes around, and then goes back out. All right, a little better. So current's going to come in, and it's going to go this way, this way, this way, and then back up this way. So if we look and do the right-hand rule, and let's say we do the right-hand rule at this spot first, my thumb would be pointed in the direction of current, so that would be up, and then my fingers, again with my right hand, would be wrapping around the back towards the front. So my magnetic field would be like that, coming from behind it over the top and in. All right, now if I do my right-hand rule here, my thumb is pointed in that direction, and my fingers are, again, they're coming from back behind it, up over top of it. So it'd be wrapping around this way. So it'd be going up on the outside of the loop and down on the inside of the loop. Same thing here, up on the outside of the loop and down on the inside of the loop. Over here, we can do the same thing, point my thumb down now. And now my fingers are, again, wrapping from this side up and over this way. So it's, again, going up on the outside, down on the inside, and then the same thing would happen here. You do that right hand rule, it's going to go up and around and down on this side. So it's up on the outside, down on the inside. So evidently everywhere we go, you're going to have that sort of thing where it's going up on the outside and down on the inside, up on the outside, down on the inside like this. And if you go through and do that, what you'll get is a whole bunch of magnetic fields that are pointed up when you're on the outside here on the edges, and they're pointed down on the inside. And if we do this loop from the side, let's say we have this is our loop, right? We kind of draw this loop from the side. What you'll end up with, here's our loop, is again these are going around like this. These magnetic fields are going like this, right? And of course, the further out you get, they just get a little weaker, but they're wrapping around this way. Okay? And what is this kind of starting to look like to you? If you think about this, you think back to last time, it should look a bit like when we had a bar magnet, north-south. It was flowing up and around like this, right? That's what our bar magnet looked like, isn't it? And so what you have is the first real kind of indications of how magnetism is formed. We have or how these bar magnets form. That should tell us that if we move charge in a circular loop and we get a magnetic field that matches that of a bar magnet, we've got to have some sort of charges moving in little circular loops over here. And it turns out, if you think about it, think down to an atom. You have a nucleus, and then you have a little electron orbiting around it. Well, that's an electron going in a circular path, kind of like this. And so just an atom, if we look at it on end, here's the electron orbiting around that way. Just the atom itself, from the orbit of the electron, is going to create a little, a little north-south magnet, right? We're going to get a little north-south magnet like that going on here, okay? And, we get a little north end and south end of a magnet, just like what we saw here. And that basically gives us what is called diamagnetism. And it turns out this kind of magnetism always reacts opposite to the magnetic field that's applied to it. And when we get to a later video and we talk about flux, then that should make more sense. But essentially, anytime you apply a magnetic field to this, what this does is it adjusts the orbit of the electron to create a magnetic field that's in the opposite direction. So this is actually always a repulsive magnetic force. If you get this strong enough, you can levitate things, and you can look up videos on YouTube, look up diamagnetic levitation. You can see like frogs being floated and fruit being floated and stuff like that, just in a really, really strong magnetic field. Now normally this effect is very weak, but there's no limit to how strong it can become. So if you ramp up your magnet strong enough, then this will ramp up and eventually become very dominant. This is usually, though, at small magnet fields, it's such a small force that it's negligible and you don't even worry about it. It only really comes into play at really big magnetic fields. So then what makes the other kind of magnetic fields? Like, how do magnets attract? If the orbital electron makes them repel, and again it's very light most of the time, well then the next thing is just looking at the electron itself. The electron itself has what's called a spin to it. It has a bit of internal angular momentum that the electron spins. So if you think about the electron spinning, it's like a little bit of charge just spinning in a circle, and it creates a little north-south magnet. And this magnetism is actually the thing that's responsible for most of the magnetism you see, the earth magnets, the solid magnets you stick on your fridge, magnetizing up paper clips, things like that. And it's called either ferrimagnetism or ferromagnetism. The ferromagnetism, they're usually used interchangeably. There's a slight difference. Basically, you go in and you look at your atom and you look at how many upspin electrons you have or your molecule versus downspin electrons. If you only have upspin electrons, then it's called ferromagnetism. If you just have an imbalance where you have up and down, but you have more up, let's say, then it's called ferrimagnetism. So they're usually used pretty interchangeably. This is the one that's most often the case, but this seems to be the word that's most often used, is the ferromagnetism. Okay? Now let's take this one step further. let's, instead of just having a single loop, let's make a coil of wires. So if we coil around a coil of wires, something like this, right? All right, coil of wires, and we're going to run electricity through it, and then the electricity is going to come out down here, our current. This is going to just take a bunch of these small little fields, and we're going to basically stack them on top of each other, and it's going to take and stretch these fields out real long like that. And so what you're going to end up getting is magnetic fields run through the middle, and then they loop up around like that, right? And it's going to loop up around like this. And this should look a lot like, more like that of a bar magnet or Earth or something like that, right? So we're actually creating these magnetic fields, and dependent upon which way the electricity is flowing, will determine which end is the north and which end is the south. The way I have drawn this now, this is the north, this is the south, because they're coming out of the north end and going around the south. But this should also indicate to you why we cannot have a monopole. Why can't you just have a single north and a single south? And because all you have to have is just one little loop of a single charge going in a circle. And it's kind of like having you can't have a circle with just one side. Like if I had a coin, like I had a quarter or something like that, I had this quarter, and I took and sliced it as thin as I could down the middle. I'd have two thinner, discs, right? I'd have two thinner discs at that point, but they'd both still have a top and a bottom. It would just be a new top and the bottom. The middle would become the bottom of this coin, and the middle would become the top of this coin. And no matter how thin you slice it, you still have a top and a bottom. If something's going on a circle path, it's going to create a north-south at the same time. And it's because of magnetic fields being created this way that happens. So it should make a little more sense to you as to why you can't have just a single north or single south pole all on its own. Okay? Oh yes, we need to do our right-hand rule. Sorry, that was a lie. I was about to say we were done, but we've got one more right-hand rule here. Our right-hand rule 3, and that is that you wrap fingers. This is for solenoids like this, or a circle of current. Wrap fingers in direction of current, right? And thumb points north. Okay, so let me show you. I've got a little picture here for you of it. This one, I believe, there it is. So as you can see in this picture, the electricity is flowing up and around, right? So this one comes up and goes down. So if we were going backwards, it'd be doing something like that, and back around this way. And you can see they've got their finger wrapped in the direction. I really think this line should be coming up and doing this. I gotta get on that line. It should be coming up and wrapping around this way. I don't think, maybe I didn't look at this carefully enough, but this wire should come up and wrap around the front here. There we go. And so then it wraps around the back to front, 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 like that. And now you're wrapping your fingers in the direction of the current, and your thumb's pointing out north. This would be the north side, so the field lines would be wrapping around this way, out of the north and back around into the south, and then up through the middle, forming those loops of magnetic field lines, right? Now you have to be careful with this, because two things can affect which way this turns out and which way you wrap your fingers. One, you can flip the direction of the current. So let's say we flip this around so that the current was going the other way. Well, then this would have to be turned around. You'd have to flip your hand around so your fingers wrap the other way, and then this would be the north side and this would be the south side if that happened. The other thing is, let's say we still had the current coming out of this side, right, and going into this side. Well, then you have to be careful about which direction is this wrapped, because you can imagine if this, instead of being wrapped around the front towards back, if it was wrapped back to front, right, so let's say it came up and it wrapped around back to front, more like that way, right, where this was our object, and maybe I can draw that a little better. So let's say we had our object like this, and it wrapped around the back and then like over the front like this, and it wrapped over the front and behind the back. Okay? If it did more like that, and the current went this way, still going the same way from this right side to the left side, you'd still have to flip your hand around because now the current is wrapping the other way. And so that would change it so that this would be the north side, and this would then be the north side, and this would be the south side. So either flip the current or change the direction that you have this wrapped, and that'll switch which in the north-south is. So be very careful with this one. It can be a little tricky. I see a lot of students messing up on that one. Spend some time trying to think about that one for a bit. Okay, I think that's pretty much everything for this video.